In today's discussion, we'll do force on a current carrying conductor kept in a magnetic field. What is the direction of the force and how we can find the direction of the force on the current carrying conductor in the magnetic field. We'll also take two straight current carrying conductor which are kept at some separation. We'll try to find out what is the force between them, what force they are experiencing. From that we can define ampere, that we can get the SI definition of current. We'll also do force and torque on a rectangular current carrying loop kept in a uniform magnetic field, because that one will be the basis on which moving coil galvanometers are designed, and that is the basic theory behind that. So we'll be doing all these in today's discussion. We want to find expression for the force experienced by a current carrying conductor which is kept in uniform magnetic field. Now for that, we assume that we have a conductor of length L which is carrying current I, and capital A is the area of cross section of the conductor. Let's also assume that small n represents number of free electrons per unit volume of this conductor. Suppose we have an electron here, and this electron is suppose moving with its drift velocity Vd. Remember that the direction of the movement of the electron and that of the current, that will be opposite, because electrons, if we assume that it is moving in this direction, then current will be moving in the direction, say, left to right, because the direction of the current we take the direction in which positive charge carriers will move. So it will be just opposite to the direction of the flow of electrons. So if I take small e as the charge, magnitude of the charge on the electron, Vd is its drift velocity, and B is the magnetic field in which this conductor is kept. So in this case, the force experienced by each electron, that will be given as your E, Vd cross B. This will be the expression for the force experienced by each electron or free electron there. So it is the force experienced by each free electron. It is this. Now, if we have taken L length of the conductor and area of cross section is capital A, so the volume of conductor, that will be equals to A into L. Number of free electrons in this conductor of length L, that will be N into A into L, because the volume multiplied by number of free electrons per unit volume. Therefore, if we have force experienced by each electron as minus E Vd cross B, therefore force experienced by all electrons over the length L, so that we can take as the force experienced by all free electrons in conductor of length L. This will be minus E Vd cross B into NaL. And this is also the force experienced by the conductor of length L, because whatever force the free electrons of the conductor will experience, same force will be experienced by the conductor also, because the conductor is having those free electrons inside it. So in this case, it is your minus EVD cross B NaL. Now this is can be written as your NeAVD B into L, or we can write minus NeAL Vd cross B. Suppose we write this one as minus NeAVD into L cross B. Now you know that I is NEA VD. Expression for current is your NEA VD. Now you just see here this term electron, and if you take its drift velocity, electron having negative charge is moving in this direction with the drift velocity Vd. If you consider the current will be moving in opposite direction to this, the flow of the electrons. So the current direction is this, and the current element that we can take as the direction of the current there. So in fact, if you take E and Vd, this will be your IL. That means the current, if it is moving in this direction, electron, if suppose it is moving in leftward direction with the drift velocity Vd, this is equal to the current element IL. So here, if you substitute this, in that case, what we'll get? We'll get IL cross B, because I was your NEA VD, and minus E VD vector we have written as your IL vector there. So in that case, you'll get this expression. That means we can just correlate it with the direction of the current element there and magnetic field. That means the force will be given as IL cross B. So this will give you the direction of the force experienced by a conductor of length L, which is kept in a magnetic field B. Again, you can see that as it is a cross product of two vectors, you can easily apply cross product of vectors. That means direction by using either a right hand screw rule or right hand thumb rule there. So you can get the direction of force. Magnitude, you can get it from this expression, ILB sine theta, and you can get the expression for the force from that. And direction by using right hand screw rule or right hand thumb rule. We also have Fleming's left hand rule to find the direction of the force on a conductor which is carrying current I and is kept in a magnetic field. And here we assume that the current is in perpendicular direction to the magnetic field. So for finding this, we stretch forefinger, middle finger and thumb of our left hand in mutually perpendicular direction, so that the forefinger is in the direction of magnetic field, middle finger in the direction of current, and thumb then will represent the direction of force. This is very important because using Fleming's left hand rule there or cross product of vectors, you can find the direction of the force experienced by current carrying conductor which is kept in a magnetic field. Suppose we want to find force between two straight current carrying conductor which are kept at some separation in vacuum. So let's assume that X and Y represents two straight conductors of infinite length. They are kept at separation D and they are carrying current I1 and I2. We want to find what is the force experienced by these conductors. Now here we are taking the case when the two are carrying current in same direction. It may be given for opposite direction. If you know how we can find the magnetic field, how we can find force, for this case, you can easily apply it for the other case also. So let's take now that B1 is magnetic field due to I1 at position of Y. That means second wire or conductor. So magnetic field due to this, as it is a straight conductor, we have assumed it to be of infinite length. So it is your mu naught I1 by 2 pi d. This is B1. This is the magnitude. Now we want to find the direction. So for finding the direction, we'll apply right hand thumb rule there. That means if we put the thumb in the direction of current, then curled finger will indicate the direction of field. Here the student gets slightly confused that how we should put the right hand there. I will just suggest that put your thumb in the direction of current. That we can easily put. Now with the tips of the fingers, you try to touch the point where you want to find magnetic field. So here, as we want to find magnetic field on right side, because Y is on right side of this I1. So in that case, we'll put our hand in this way so that the tips of the fingers are touching the point where we want to find magnetic field, thumb being in the direction of current. So the tips of the finger is indicating direction into the plane. So the direction of magnetic field will be into the plane. So this is the direction of B1. So this is into the plane. There is another one that is called as the right hand palm rule, where we put thumb in the direction of current and we put our palm straight. By right hand palm, we try to cover the point where we want to find magnetic field. Then the facing of the palm will indicate the direction of magnetic field. So here, as we want magnetic field on right side, we'll put thumb in the direction of current and we'll put our hand like this because we want to cover the point on right side. So we'll put our hand like this. The facing of the palm in this case is into the plane. So the direction of magnetic field will be into the plane. Now, if I take F2 as force experienced by L length of Y, that means the second conductor, which is carrying current I2. So for that, because now you have a current I2 through the wire Y, and it is kept at a point where magnetic field is B1. So obviously you have now a current carrying conductor kept in a magnetic field. So we can find the direct force experienced by this. So this is your I2L B1 sine pi by 2, because the angle between current and magnetic field is perfect, 90 degree there. So this is your I2L. Now for B1 I can put mu naught I1 by 2 pi d. So this is your mu naught I1 I2L by 2 pi d. And now what will be its direction? For finding direction, we'll put our forefinger of the left hand in the direction of magnetic field, that is into the plane. Middle finger in the direction of current. Then thumb will indicate the direction of force. So if you put the left hand in that way, you'll find the direction of the force will be towards X. So this is your direction of F2. So this is directed towards X. This is your F2. Suppose I call it as equation number 1. Similarly, we can take B2 is magnetic field due to I2 at X. So this will be mu naught I2 by 2 pi d. Now you take the direction of this one. So for that we'll put our right hand in this way. If you are using right hand thumb rule, we'll put our thumb in this way, and now the point of observation is on left side, so we'll put our hand like this. When the point of observation was on right side, we have put our hand like this, so that tips of the finger will be touching the point where we want to find magnetic field. And here we'll put our hand like this. Now the tips of the finger is indicating direction out of the plane. So the direction of the magnetic field will be out of the plane in this case. So this will be the direction of magnetic field, and this is your out of the plane. You can also apply right hand palm rule there. In that way, we'll put our hand like this so that facing of the palm is on out of the plane direction. So in that case, it will also indicate the direction out of the plane. So this is mu naught I by 2 pi d directed out of the plane. Now we take F1. This is force experienced by L length of x. So in this case, this is your mu will be equals to I1 L B2 sine pi by 2, because I1 is the current through first wire, magnetic field at its position is your B2, length is L, angle is 90. So this is your I1 L mu naught I2 by 2 pi d. So this is your mu naught I1 I2 L divided by 2 pi d. And what will be its direction? We'll put our forefinger in the direction out of the plane, middle finger of the left hand in the direction of current. So in that case, the thumb will indicate the direction towards second wire. So that means this will be the direction of the force experienced by first wire. So this will be towards Y. So this is your second. So what we find, the force experienced by second wire is towards first wire, and that experienced by first is towards second wire. That means both are experiencing force towards one another, or you can say that the force is attractive. So if the current is flowing through two wires in same direction, the force will be attractive in nature. Also, as the direction of F1 and F2 is opposite, equal in magnitude, then it is obeying your Newton's third law also. In general, for the force experienced by L length of the conductor, F as mu naught I1 I2 L by 2 pi d, or F by L is mu naught I1 I2 by 2 pi d. That means force per unit length of the current carrying conductor will be mu naught I1 I2 by 2 pi d. We use this expression to give SI definition of current. Unit of the current is ampere. So the SI definition of the ampere is done or is given by using this formula. Now what we do here, if I take I1 equals to I2 equals to 1 unit, and D is also 1 unit, then what will happen? F by L will be equals to mu naught by 2 pi, and this is your 2 into 10 to the power minus 7 Newton per meter. So SI definition of ampere we can get. It is the constant current which when passed through two wires of infinite length, negligible area of cross section, placed 1 meter apart in vacuum, which will produce a force of 2 into 10 to the power minus 7 Newton per meter length of it. So from this we get the SI definition of ampere. Let's now discuss force and torque experienced by a rectangular loop which is suspended in a region of magnetic field and is carrying certain current. So let's assume that we have PQRS as a rectangular loop of length L, breadth B, suspended in a region of magnetic field B. This loop can turn about an axis XY. So now if I assume that F1 is force experienced by PQ. So it will be your ILB sine theta, because I is the current, L is its length, and B is the magnetic field, and the angle between the two is theta there. So here this will be ILB, and now if you take its direction, so we'll rotate it from the direction of current to magnetic field. So if you turn it in the direction from current to magnetic field through a smaller angle, the direction of F1 will be in this direction. That is in the direction XY. So this F1 is along XY. Let's call this as equation 1. Let's take F2 as the force experienced by arm QR. This. So again, this is your I, B, B sine pi by 2. Now this time the current and magnetic field, if you consider B is in this direction, current is in this direction, angle is 90. So in that case, it is your IBB sine pi by 2. And this is your IBB. And what will be its direction? From current is in this direction, magnetic field is this. So if you rotate a screw from current to magnetic field direction through a smaller angle, in that case, this will give you the direction into the plane. So F2 is directed into the plane. So this is directed into the plane. Let's call this as equation number 2. F3 is force experienced by arm RS. So this is your ILB sine pi plus theta. Now why it is pi plus theta? Here if I have measured the angle, suppose in this direction, that is we have measured it positive in the clockwise direction. Here also if you have the magnetic field in this direction and the current is in this direction, and if you measure the angle now there, this is theta, so this is your pi. So obviously it will be pi plus theta, because whenever you are measuring angle, whatever direction you take, in that particular problem, in that particular case, you should adopt only one sign convention. If you have taken clockwise direction of the measurement of the angle as positive, let it be positive for all cases. If it is anti-clockwise direction you have taken positive, let it be for all cases there. So here, this will be the ILB there into sine theta, and this is your along XY. Remember, if you take the direction, it will be F3. Either magnitude wise F3 will be in the upward direction Y to X, or with negative sign if you write, it will be in the direction X to Y. Okay, so this is your third. And F4, this is the force experienced by arm SP. So this will be your again IB B sine pi by 2, or it may be your 3 pi by 2 you are taking. In that case again it is your IBB, and now direction, magnetic field is in this direction, current is downward. So in this case if you rotate it from first vector to second through a smaller angle, the direction will be coming out of the plane. So F4 is in this direction. So this is directed out of the plane. This is the fourth one. So now we have got expression for the force experienced by all the four arms of this rectangular loop. So we can find out net force. If this will be your F1 plus F2 plus F3 plus F4. And if you substitute the value, it is your ILB sine theta, IBB directed into the plane, minus ILB sine theta for the third one, and for the fourth one, IBB out of the plane. So now you can see this one is plus, this is minus. So we can cancel. This is into the plane, this is out of the plane. Again, they will get cancelled. So the net force will be 0. So net force on the rectangular loop carrying current and suspended in the region of magnetic field will be 0. Suppose we want to find torque experienced by rectangular current carrying loop in the magnetic field. So here, how will you get the torque? F1 and F3, they are acting along the same axis, along the same line. But of course, they are in opposite direction. So as they are along the same line, in that case, they can't produce torque. So it will be 0. Torque will be produced by the pair F2 and F4 forces. So F2 and F4, if you consider, they will be giving you the torque in this rectangular loop. So torque experienced will be force into perpendicular distance. What is this force? Force, that is F2 and F4. So this will be your IBB. Now if 2 is here, F4 is this. Distance between the two is L. The perpendicular distance between them will be given by this one, L cos theta. So if you put it here, it is L cos theta. That way, the torque value, what you will get? ILB B cos theta. L into B, I can write it as the area. Now, this is the expression for the torque. If you want to write that in vector form, can we write it like this? Torque is your I A cross. Now here, if I just convert it in the vector form, it is your cos theta. So it should give you dot product. Then you will get AB cos theta there. But if you take dot product, then it will be a scalar quantity. Left hand side is a vector quantity. So obviously this is not the correct way to express. But as it is cos theta term there, you can't take it cross there. But there is one thing. If you take vector area will be always perpendicular to the plane which is containing it. So the direction of the vector area will be this. So the angle between vector area and magnetic field is not theta. This is something else. Suppose I take this one as a phi, the vector area, and this is the direction of the magnetic field. If I assume that this angle is phi, then theta plus phi, what will it be? This is your pi by 2. So now this theta will be pi by 2 minus phi. And then if you take for cos theta, this is your cos pi by 2 minus phi. And that is your sin phi. So I can write this expression for torque as IAB sin phi. And if you have written in this form, definitely torque in vector form, you can write it as your IA cross B. Because here phi is now angle between vector area and magnetic field. We cannot write that one as A dot P because theta is not the angle between vector area and magnetic field. For coil of N turns, the torque will be given as your NIA cross B. So this is the expression for the torque on a rectangular coil suspended in a region of magnetic field and it is carrying some current.